This panel will be, the potential of negative emission hydrogen from using biomass. And I know you guys might be tired, hungry. It's lunchtime, but me and my team will work really hard to make sure this is a fun session for you guys. So first, I'm Wenqin Li. I'm a staff scientist from Lawrence Livermore National Lab. I worked on the BiCRS chapter. I led the BiCRS technology section for the roadster removal study. Actually, we have more, BiCRS chapter authors, Alvina, Hannah, all here. Ask them the hard questions. And today, I am very happy to moderate this session with, all the experts from different sectors, have them to share their insights, experiences, challenges for this, negative emission hydrogen topic. I want to start with, a brief introduction of everybody. So we have Josh Stoddard first, the co-founder and CEO of Moat. We also have David Edward, the director and advocate for hydrogen energy from Air Liquide. We have John Walls, a Carl V.S. Partisan professor from of chemical engineering of University of Pennsylvania. I'm pretty sure it means a lot there. We also have Robert Schressingost, the division director of hydrogen waste carbon management from DOE. So I'm glad to have everybody here to have like a discussion on this topic. But before we started our discussion, I just want to quickly highlight, what do we have fun for BiCRS from the roadster removal study. So our lead author, JP, has done a great job, giving you an overall picture of what do we have achieved and fun from the roadster removal project. And specifically for BiCRS, we have found that United States actually has a huge potential for waste biomass that, if we use it smartly, we could achieve more than 800 million tons of carbon dioxide removal per year. With a cost of less than $100 per ton. And this is all estimated, based on assumptions of no impact on cropland and food production, which is quite important to this topic. So biomass, a lot of you might be very familiar. I just want to say that biomass is a very interesting source because it can not only help us remove carbon from the air, but also it provides a variety of products that we could use that we need today and we might still need it in the future. So from the biomass capacity we have estimated in our study, we analyze over 27 different BiCRS pathways because we know, acknowledge there would be some competing interests among the use of biomass for different purposes. So from our exploration of that 27 different BiCRS pathway, we found that biomass to hydrogen waste carbon capture and storage actually stands out as one of the pathways that has the lowest carbon removal cost because it can remove the highest amount of carbon dioxide per ton of biomass. And also it produces a very valuable product that the market needs, which is, what are we talking about here today, the negative emission hydrogen. So from our study, we estimated that we can not only remove more than 800 million tons of carbon per year from the atmosphere, but also we can produce around 34 million tons per year of negative emission hydrogen at the same time, which is 70% of the total US demand for hydrogen that has been projected for 2050. So that's quite promising. And here today, we're in Pennsylvania. Pennsylvania is actually a pretty good fit for BiCRS because you guys have a lot of biomass and also have suitable carbon storage, which are both very important for BiCRS. We have estimated that Pennsylvania has, I think, around 14 million tons per year of biomass that's available. And that could, provide a carbon removal potential of 23 million tons per year and a negative emission hydrogen production potential of up to 1.8 million tons per year. So it's quite a bit. So back to this, panel discussion. how can we really harness the power of the biomass to help us not only remove carbon, but also produce, the hydrogen product that we really needed. I hope, today through the discussion with all the experts and you, we could, have some ideas about how we can all work together to accelerate the deployment of BiCRS to produce negative emission hydrogen. So with that, I'm going to start to hand over to my dear previous colleague, Josh Stollerf, who is now the Mode CEO, to share his story about negative emission hydrogen production from biomass in California. With that, Josh.
Thank you. So I had the good fortune to work on the predecessor report to getting to roads removal, which was getting to neutral. And it was my conclusion in that work, much like Dr. Lee just said, that the best option for carbon removal, most scalable, lowest cost, was biomass gasification to hydrogen, and especially waste biomass gasification to hydrogen. So I left the lab to found Moat 3.5 years ago, and we've been working to commercialize just that. So let me tell you a little about the process. So we can take biomass waste, and in California, we're focused on agricultural residues. We have a lot of orchards. There's orchard tree trimmings. There's nutshells, fruit pits. But we can also use forest residues, like we've heard. That's very important to utilize, like the brush and small trees that get cleared for fire prevention. And we can do urban green waste, construction, demolition wood. All of this stuff can be gasified, and that's one of the great advantages of the technology, that it is flexible in terms of the feedstock. So gasification is you heat up the stuff with limited oxygen. If you heat up biomass with excess oxygen or with air, you get combustion. That's just burning it. If you heat it up with limited oxygen a bit, you get pyrolysis reactions. You can get biochar and liquids. If you keep going up in temperature, and for us we're at 850 centigrade, you turn everything into gases. So that's gasification. And then with a bunch of downstream technologies that we already have, you can turn those gases into hydrogen and CO2. At Moat, we put the CO2 underground. So we're taking carbon that the plants got out of the air for us. They did that really nice service, and we put that underground. And we take the energy value of the biomass. Hydrogen is stored energy. It's more valuable than electricity because of that. And we can deliver that for customers. In California, we're talking mostly about transportation use of hydrogen. Heavy-duty trucks, buses, port vehicles, all that stuff. So this is a great way to do carbon removal, but the magic of it is you get these three value streams at once. You can do the carbon removal, you can make clean energy, and you can do waste management. So that makes this approach really compelling. We've got a couple of commercial projects in California. One of them is funded in large part by the California Hydrogen Hub, which is called ARCHES, and we'll be making hydrogen as part of that and putting CO2 underground near Bakersfield in California, operating starting in 2028. So thank you very much.
All right, thanks, Josh. So next, start with David. Can you tell us a little bit more about the hydrogen activities in Air Liquide?
Yeah, certainly. You can't go. Is that on now? You can't come to a hydrogen or an energy workshop or an environmental workshop without there being a panel on hydrogen these days. It's reached its sort of peak, its 15 minutes of fame, as it were, but it's going to lead to many, many years of transformation of our energy sector, potentially. My name is Dave Edwards. I'm a director and advocate within the hydrogen energy business of Air Liquide. If you know anything about Air Liquide, we're a very large international company, 60,000 employees, $30 billion of revenue, focused mostly on gas separation processes, historically air separation, hence our name. But hydrogen, for the last 70 years or so, has been a core business of ours. But that hydrogen is focused around the industrial sectors, taking methane, splitting it with steam methane reforming or other similar thermochemical conversion processes, and then selling that through pipelines, compressed gas, or liquid form to things like refinery applications for desulfurization, to ammonia industry related industries for agricultural products in general, and to other specialty chemical, metals, and other applications. I'm in the hydrogen energy business, and for us, that means something different. That means consistent with reducing environmental footprint for our customers and entering into new markets, in particularly the transportation sector, using hydrogen as a transportation fuel. In order to do that, we have to reduce our carbon footprint, and the ability to go to removal of carbon leads us down a pathway of the thermochemical conversion of hydrocarbons or biomass into hydrogen. We heard already a little bit about taking solid biomass and converting that through gasification and the challenges that we'll be faced with doing that. For our industry, we spend a lot of efforts on taking biogas, which is renewable natural gas from sources like wastewater treatment, from landfill gases, and from aerobic digestion, upgrading that to pipeline spec natural gas, and then putting it into the same reforming systems that we use for our hydrogen production. That can actually get us to a negative footprint of carbon intensity for that hydrogen production. And you can go further negative if you add carbon capture to the back end of those same processes. The production of hydrogen from a hydrocarbon obviously produces a significant amount of CO2 in a fairly concentrated form that is relatively open for carbon capture technologies. Across that spectrum of technologies, we do all of the separation technologies. We do the upgrading of biogas at landfill sites and digesters using things like membrane separators and adsorbent-based processes. In the hydrogen production facilities, we do the thermocatalytic conversion of methane molecules, water gas shift, and the other processes related to that. And then on the downstream side, the plethora of technologies usable for carbon capture, including cryogenic separations, adsorbent and amine-based systems, are all part of the technologies that we offer to the markets. With that, I look forward to the conversation, and I can be the reference for the industry sector of things that have already been happening in the hydrogen world and how the challenges of real-world applications apply to some of these solutions.
That's great. Thanks, David. We want to hear more about how the real world works about the hydrogen topic. Next, John, you are a professor at University of Pennsylvania. Can you talk a little bit about the workforce development needs for this emerging industry?
Sure, I'd be happy to. Let me give a little bit of background. So I'm a professor in chemical engineering, and my research interests sort of intersect with what we're doing here. I do a lot of work on biomass upgrading, producing hydrogen as one product, but also electrochemical systems for like water electrolysis and hydrogen production. One thing I think that this pervades all the discussions we're having today. You have to think, if we want to commercialize these technologies, you know, what workforce do you need and what skills do you need in a workforce to do that? We heard from David sort of that the downscale side processing, or up, you know, after you've done the biomass gasification, a lot of that standard chemical engineering and sort of chemical engineering skills are needed. But then we start thinking about the biomass side of it. That's solids processing, that's pyrolysis and things. And these are subjects that are touched upon as sort of standard engineering curricula, but they're not sort of mainstream in the curriculum. And part of the reason is that the underlying science in terms of thermodynamic chemistry, that hasn't changed over the years. That's the same. But we tend to use, at least at the undergraduate level, we tend to use textbooks that have been optimized over the last 50 years. But like in chemical engineering, they've been optimized from a petrochemical perspective. So they tend to focus on, we heard like membrane separation. They don't do that. We do distillation because that's what you need in a petrochemical refinery. You don't do so much on solids processing. And these books have been upgraded to sort of, they have applications in these areas, but it always comes across as an afterthought. And I think if we want to excite our students to work in these areas and really get them well trained so they can, right when they get on the job site, they can start participating and having an impact, we really have to understand these technologies and sort of the, in chemical engineering term, the unit operations that are involved in these systems right from the very start, which I think really, as an educator, and saying my colleagues at all universities, need to really look at this, where things are going, especially in the chemical industry, and how we upgrade our curricula. And part of that is, you know, people need to write new textbooks and those types of things that are difficult to do. So I'd be happy to answer any other questions from the audience on this subject.
Great. Both Josh and David needs your student. Last but not least, Robert, can you share a little bit more about the DOE activities around hydrogen?
Certainly, I'm happy to. And thanks for the opportunity to be here today. I greatly enjoyed working with Jen for 3.5 years in my tenure at DOE. I've only been there about 4 years. I came from GE Power and Alstom Steam Power. So I'm a reformed coal guy trying to atone for my past sins. And JP's little video did really hit me too, because I had my first grandchild 5 weeks ago. So like the future of the planet is very much in. So I'm really happy to be at DOE and being able to participate in this clean energy revolution. So the gasification program is one of my programs under hydrogen with carbon management. It's my main hydrogen production program. And we really pivoted 3.5 years ago to making net zero hydrogen by co-gasification. Careful to not sound like coal gasification, but co-gasification of biomass with waste streams, even legacy coal waste, petcoke from refinery operations. MSW is a big one we're looking at right now. Unrecyclable waste plastics, a lot of processing required there. So we've had a FOA called FO 2400. It's kind of famous in DOE because we opened it about 5 times and we made like $150 million of awards under it for all of our departments. But the gasification program now has $45 million in projects under execution. Our feedstocks include, woody biomass, agricultural waste, MSW, slurries of pulverized coal and liquefied plastic oils, construction and demolition waste, forest management waste. So really, we're looking at all the feedstocks that we've talked about there. This week, NETL, our National Energy Technology Lab, which is our applied lab for power production, they're kicking off a newly formed gasification National Lab Consortium. The members include National Renewable Energy Lab, Idaho National Lab, and Oak Ridge National Lab. It's led by NETL. One of the main things we're really looking at there is to develop a kinetic database of gasification kinetics for all these widely disparate feedstocks, because they all have different kinetic parameters, and to be able to optimize the gasifier design, the more you know about the kinetics, the better. And then there's also a lot of work in feedstock prep. We're developing standard recipes of different waste streams and different biomass streams. We're having Idaho National Lab produce those so we can get those samples and do the kinetic work on them. Gasification is not the only thing we do. I also have turbines in my program. So advanced turbines, we're looking to decarbonize those. We just put out a notice of intent for a FOA that we plan to issue in the future on zero carbon gas turbine demonstration. So those will involve either hydrogen firing, 100% hydrogen firing, a fuel that's recently become attractive because of its cheap transportation costs is ammonia. So we're actually doing direct ammonia combustion testing right now, or partially reformed ammonia fed to gas turbines. And again, we have an ammonia combustion working group, again, led by NETL. And this is open to academics and commercial interests. We have bi-monthly meetings, researchers share experiences. It's all very collegial. If anyone's interested in that afterwards, take my card and I can get you in touch with the right person there. I also coordinate our work with like the Hydrogen Fuel Cells Technology Office, some of the other offices, and we've started to do some collaborative funding. So right now we have an Industrial Energy and Decarbonization Office, FOA, that is under merit review. We're co-funding pre-feeds for industrial decarbonization through hydrogen production. So looking at pre-feeds at specific sites with specific hydrogen production technologies to see how those might be feasible and the costs associated with that. Workforce development, but community engagement are also very important. And so Hydrogen and Fuel Cell Technology Office also had an equitable hydrogen development FOA not too long ago. And we did fund a community benefit plan case study under that as well. We're, for a Fallensby, West Virginia, an energy community, and the ARCH2 hub. So we're trying to look at all these different aspects. I do want to talk about one real big win that we've had recently, and Julio said you can't just decarbonize, you got to build stuff also. JP actually had it on one of her slides, the Wabash River gasification plant. So that was funded completely by our Office of FE20. So my other associates are here today, Marina, Rory, we all kicked in money for this. It was too big to fund from one program. So it was a $47 million pre-feed and feed project. We looked at it's repurposing the retired Wabash gasification plant in Terre Haute, Indiana, to be a clean hydrogen production facility. So we looked at a lot of stuff in the pre-feed. We looked at power production. We looked at all kinds of feedstocks. We kind of settled down under the feed to do ammonia production because it's right in the heart of agriculture area, and it's actually supply constrained there. Ammonia is tough to get right there now, so costs are high. So that's what we ended up with. So we ended up with designing a system that would make 500,000 tons of low carbon intensity ammonia per year. The LCA by a measure determined by Oregon National Labs in their GREET model was 0.38 kilograms per kilogram ammonia. So very low, and it's going to sequester 1.6 billion tons of CO2 a year. So our feed study gave them enough information to obtain their air permit, obtain their permit to construct their facility, obtain their permits to construct their Class 6 injection wells. They have 2 Class 6 wells permitted and allowed to construct now. So all that was great. But then Monday I heard they got $1.56 billion from the Loan Programs Office. So first quarter of 2025, they will make a final investment decision to proceed with this project. So like we gave them seed money. They worked a long time to find the right business case and the right mix of feedstock and products, and they came out with a hugely successful project. And that's, to me, like building stuff, steel in the ground, that's where we have to get today. You know, we've done a lot of R&D, now it's time to deploy. So like to highlight that success, and thanks for listening.
Great. Thanks, Robert. Seems like a lot of programs are already acting, and hopefully more is coming. Following up on that, now is a fun time. It's a question time. I have only 2 questions, so audience, you guys got to work hard and torture them. Okay, they fly here, caused all those emissions. Okay, my first question is, we're talking about hydrogen here, and specifically gasification to hydrogen plus CCS. Josh and maybe David can chime in too. You know, as a smaller business versus a larger business, do you feel, you know, what is the hydrogen policy support that you would like to have, or you already have, you feel appreciated for? And the next question is, what would you like to have? That's, you know, some homework for Robert to take home.
So in many ways, we have like a first in history opportunity right now for doing biomass to hydrogen projects, because we have clean hydrogen incentives with the Inflation Reduction Act. In California specifically, we have the low carbon fuel standard, which is really helpful. And we've got even private markets for carbon removal. All of these things help make a project and are helping make our projects go, not to mention all the DOE support getting some of these things off the ground. What we don't have very much yet is a recognition that BiCRS is carbon removal. We don't have that in the federal 45Q credits. And we don't have that in too many markets for carbon removal. Of course, we need more markets for carbon removal overall, but like this idea is kind of new. I mean, I think we kind of popularized it in 2020 and after. So still a lot of folks in government and policymaking positions just that don't know what it is, don't know that you can make hydrogen and do carbon removal at the same time. So we definitely could use more support for the most important part of what we're doing, which is getting CO2 out of the air this way.
So if I were back 5 years ago, this would be a really short conversation as to what we had in place. It would be a few things in California and not really much anywhere else. But that has radically changed now in the last few years. The IRA, the IIJA have provided opportunities through the hydrogen hubs and through the incentives for tax incentives for production. I can't agree more that the the need for incentivizing removal of carbon doesn't really exist in those policies. In fact, one of the few policies that does would be the LCFS program in California, which rewards you for carbon reduction regardless of methodology, but rewards you proportionally the amount of carbon you're reducing. And you get credits if you go negative. And so that's one of the very few programs that actually does provide an incentive for going negative, for example, although there are some boundaries as what's viable there. Low carbon credits in the LCFS program is absolutely stalling investment in California today. But what is it that we really need going forward? For a company like Air Liquide to make billions of dollars of investments, we need some assurance that the markets will exist, that the customers are going to have long-term commitments to be able to be off-takers for the low-carbon hydrogen we can produce. Are there incentives for fuel reductions? Are there incentives for the use of low-carbon agricultural products in the case of ammonia, for example? In most cases, it's those downstream markets that really lack the incentives to adopt and pay the premium that you'll have to pay for low and zero and negative carbon hydrogen. We can produce hydrogen. We can produce hydrogen at negative carbon intensities, but it is expensive. Scale will help. Investments will help. But we need that market surety to be able to make the kind of investments that enable scale and enable the cost reduction. So it really, in the portfolio of things we would ask of, it's to really focus on those off-takers to enable them to use the low-carbon hydrogens that we're producing.
Robert, is them asking too much?
Well, I mean, from my perspective, just clarity on the 45Q credit go a long way towards clearing up a lot of the uncertainties with the hydrogen hub participants right now. I've, seen in the news many of them stating that like without the 45Q V credit for their hydrogen production, like they're going to drop out of the hub. It's not working for them. So, Congress clearly intended all pathways to be involved when they wrote the legislation. They wrote credits up to the 4 kilogram CO2 equivalent limit. IRS is interpreting that way. And interesting with the Chevron decision, the Supreme Court, what's going to happen there? Who's going to win? Is someone going to bring suit to like overturn what the IRS is interpreting this as? I don't know. But I keep hearing about like 45E uncertainty is causing a lot of, that's kind of why I think hydrogen slowed down a little bit in the last year. It's still a lot of interest, but FIDs are still very slow. And I just want to note, like Wabash River is using 45Q, not 45V, because that's certain.
Great, thanks. I like this discussion. I have one last question, and then it will be you. So we talked about the challenges for policy, for the support from the government. Besides that, what are the other challenges for the negative emission hydrogen industry that you guys have seen, and how can we address that? This is just a random question, came off my top of my head, so.
So I think I can go back to the point I made earlier, and that is the assurity of the off-takers. The challenges from a policy perspective, there's a lot of uncertainty that's in there, but it really is that market uncertainty. We are trying to, and the analogy is always build the plane as you're flying it across the country kind of thing, that we need to make investments now to be able to produce hundreds and thousands of tons of low and negative carbon hydrogen in order to meet the needs that society has for decarbonizing these sectors. But at the same time, we have to make sure that there's a market to sell those into, and that doesn't exist right now. So we're actually developing the market. We're working with the heavy-duty truck manufacturers to develop that next generation of vehicles. You couldn't go out, if I gave you $1 million, you couldn't go out and buy a Class 8 vehicle that runs on hydrogen. You're going to be able to in a few years, and it'll be a lot less than $1 million. But today you can't. So we have to anticipate that market is going to be sufficient for us to be able to sell the hydrogen in the production facilities that we're investing in today. That is a very high-risk environment for the kind of numbers that we're looking at and the kind of numbers that we need to be able to invest into this market.
Josh, you have anything to add?
There's always more challenges, but thank you, David. That was well said. So I'll start with what I think is actually a huge advantage we have in this area, which is that technology, for the most part, has already been developed and it's already been scaled. Our friends at DOE spent decades developing gasification technology. A lot of private companies invested hundreds of millions of dollars in gasification projects. They didn't know they were doing it for carbon removal we just got lucky that we can take that technology and apply it to carbon removal. They thought they were doing coal gasification. They thought they were doing waste management. Now we get to do something actually 4 to 10 times as valuable with that same type of plant. So that part is great. The challenge is we still need to build something new. And big players, for the most part, with all respect, don't like to do new things because they're making money doing other things right now. So it takes startups, it takes ambitious policies, and as ambitious and small teams, it's hard to do big things. But this is actually a case where a big plant is the answer. You're doing underground CO2 storage, you're using technologies that are already scaled, like gasification and gas processing, and so your projects need to be pretty big. And so there's a challenge in financing and constructing that stuff. You know, you can get a lot of help. We get help from federal policies like the Hydrogen Hub loan program. At Moat, we're working with big partners. We have big companies that are hydrogen customers, carbon removal customers, CO2 storage partners. But all of these things come down to, we want to make a difference in the physical world. That's challenging, especially in this country. It's people and permits and policies and all sorts of things that move slowly by nature. And there are a lot of options. You can look across the supply curve in roads removal. There are a lot of carbon removal options where you can start small and do distributed and things like that, but they're not going to move the needle the way these kinds of big BiCRS projects can. So we need to put some attention on the inherent challenges in building big projects.
I guess I have one last thing. So Congress gave us $8 billion for hydrogen hubs. We only awarded $7 billion when we selected 7 hydrogen hubs. It's because as we were developing that whole program, all the different DOE offices kind of recognized that just because we build it, they may not come. So we gave $1 billion, well, we set up a program with the Energy Futures Initiative and Ernie Moniz's group now to give them the ability to design a $1 billion demand incentive program. So we're going to use that last $1 billion on demand incentives. I have no idea what they're going to look like right now, but they're in great hands with the former, head of the DOE and his organization. So I'm looking forward to what they put out for demand stimulus.
I like that hedge fund. Can I call it a hedge fund? All right, questions from audience.
We have a question back here we'll start with.
Okay, thank you, Susan.
Hi, Joe Rome with the Penn Center for Science, Sustainability, and the Media. I have 2 questions. One, I want to clarify something that was just said. I want to read a line from the roads to removal. Full-scale biomass gasification projects are yet to be demonstrated. I ran the program in the 90s. It's been 30 years. We don't even have a demonstration of a large-scale plant. We're not close to commercialization. It's entirely possible we won't commercialize anytime soon, if ever. I think it's just a point worth, posing. I think the second question I want to ask is the road removal is a very thorough analysis. I'm a very big fan of it. It has one omission. Hydrogen has a high global warming potential. And its latest analysis is it's 35 for a 20-year global warming potential. And the question is, have any of your LCAs put that number in? Because I just don't think you're going to get negative hydrogen if you look at the leakiest gas in the world with that kind of global warming potential. Thank you.
Yeah, thank you. I didn't expect the hardest question has come to me. So the short answer is we didn't. We didn't expand the system boundary to understand the other potential, like global warming potential that other products could cause. What we focused on is the net carbon in the whole supply chain, from biomass to hydrogen to carbon sequestration. And I heard a little bit more about that that statement about the concerns around hydrogen and I would love to learn more about that. Maybe we should have a lunch chat and you can educate me on that. Oh, okay, go ahead.
Actually, if I can comment to the 2 points, I think the point was made a little bit earlier that a lot of the technologies beyond just solid biomass gasification are existing, right? Steam methane reforming and replacing that with renewable natural gas is established technology for decades. Carbon capture added to that brings a new twist. That has not been done at scale other than a few at-scale demonstrations, but now looking at doing that at an industrial scale. But these are the solutions that are required. In order to get to negative carbon hydrogen, you're going to have to do these things at scale. And as much as possible, those first generation of investments will be based on extending technologies that have already been proven at scale. And that buys us the time for the second generation of investments, which will be scale up of those other technologies which have been proven at technology demonstration phases. For your second point, there's no need to do hydrogen if we don't have a net reduction in carbon emissions. And so properly capturing the effect of emissions of hydrogen into the LCA is absolutely the responsibility of good policy, of good industrial players, of the market itself, and that will over time evolve. At this point, it's not clear how we would implement that into some of the LCA calculations, but it's absolutely a topic of top concern for everybody involved.
Yeah. Thank you, David.
All right, we're going to take one more question from online. We know there's a lot of other questions here in the audience. We encourage you to find people at lunch and ask your questions. So this is our one last questions for the panel. Given that biomass conversion to hydrogen is supported by both 45V and 45Q, but a hydrogen producer can only claim one credit, not both, how are full stream partnerships being developed and structured to economically alleviate the high cost of capture for the biomass processor and the high cost of hydrogen production?
So I can say for Moat's case, it turns out the 45E credit is a bit more valuable. So it's almost $3, only lasts for 10 years. So kind of averaged out over the plant lifetime ends up being like worth $2.60 a kilogram. 45Q for us would be worth something like $1.85. So we'll choose 45V. Be great if we could do both, but that's the policy gap, is that there's no extra incentive to go negative in carbon intensity in those credit systems.
Yeah, in general, that's right. If for an equal basis, 45V is generally worth more value than 45Q for the same production facilities. But keep in mind that there's the supply chain, the complexity of these projects requires energy management, feedstock management, land management, the hydrogen production itself, the hydrogen distribution, the infrastructure assets, the off-takers, the development of vehicles, the development of markets. There are a lot of places where the IRA and other incentives stack in addition to what we might do with 45V and 45Q. And keeping in mind that we need that broad spectrum of incentives because each of those individual elements in a complex project need to be made whole. That's really where the luxury of having this breadth of different incentives really comes to play. But between 45V and 45Q, it's usually pretty obvious from a specific project evaluation perspective, which is best.
All right. Well, thank you guys for staying with us, and thank you guys, great panelists.
Before we break for lunch, I just want to make a point. Joe, you brought up hey guys, before we break for lunch, and then just before we break for lunch, I'm going to make a good point, I think. So Joe brought up an interesting point about hydrogen and leakage. And hydrogen is an indirect greenhouse gas. There's been a lot of work on this topic from the Environmental Defense Fund. When I was at DOE, we shepherded a 2-year study. In fact, that's how I met David Edwards of Air Liquide. And we specifically looked at the impact of the hydrogen economy on the potential leakage of hydrogen. If anybody wants to know more about that topic, I'm happy to share resources with you. It's really important, and that as we develop infrastructure for hydrogen, that we want to make sure it's leak tight, just like we think about methane for upstream emissions of oil and gas production. So thank you. We have lunch downstairs.